Dear students, today we are going to discuss about the filters. That is a continuation of unit 4. In this last video, we have discussed up to the constant K filters. Today we are going to discuss the remaining topic, that is the M derived filters. Normally the M derived filter means we are introducing some new notations, that's a M, in the existing constant K filter. So that constant K filter have some drawbacks. So due to that, we need to find some new filter, that is M derived filters. This was the major drawback. The attenuation does not increase rapidly beyond the cutoff frequencies. It means we can vary the frequency up to certain region, that is up to cutoff frequency only it's possible. Then a characteristic impedance, that is Z0, varies widely in the transmission or pass band from the desired value only is possible. So this, due to this drawback, so we need to find it out some new filters, that is the M derived filters. So but it is also have the same impedance, but we can vary the range of pass band and attenuation band. The degree of attenuation outside of the pass band is possible in the M derived filter. Suppose we can consider for a T network, the series arm or shunt arm has been modified with introducing some constant M. If this network have the same characteristics impedance, that is the Z0, but the shunt impedance must be modified as Z2 is modified as Z2 dash. So that we will discuss through the derivations. You can consider this is the T network and this is the modified T network. So here we are adding the M in the network. So similarly here also we are adding the M, but the Z2 we are changed into Z2 dash. That is only the different. For the prototype shown in the above figure, based on that the ZT, that is the characteristics impedance or equivalent impedance value, we know that that's Z0 T, it should be equal to the square root of Z1 square by 4 plus Z1 into Z2, that's a common expression which is obtained in the ladder circuit. For the modified network, this is applicable for this case, but we are introduced some M as well as the notation also changed. So accordingly we need to find it out the new characteristics impedance Z0 T. It should be equal to the square root of the Z1 is replaced into M into Z1 and Z2 is replaced into Z2 dash. So we are substituting the new values in the previous expression. We can obtain Z0 of T, it should be equal to M square Z1 square, the square root of M square Z1 square by 4 plus M into Z1 Z2 dash. So this Z1 square by 4 plus Z1 and Z2 has been changed like this. From this expression we can find it out Z2 dash. So the Z2 dash, it should be equal to Z2 by M 1 minus M square divided by 4M into Z1. You can find like this. See here the M is there. If suppose we are shifting LHS side to RHS side, the Z2 dash alone we are kept it in the same side. The remaining we are moving from LHS side to RH side. So you can obtain this expression. This means the Z2 dash must have the impedance Z2 by M. The series, in the series with the impedance Z1, it should be equal 1 minus M square by 4M. See here, while we are comparing this previous expression, we can find it out easily. Z2 dash must have been an equivalent impedance, that is the Z2 by M. In series with the impedance Z1, it should be equal to 1 minus M square by 4M. And this impedance can be physically reliable if 0 less than the M, similarly less than the 1. The complete M derived T network as shown in figure like this. So the M into Z1 by 2, then M into Z1 by 2. But here the Z by M, that is the newly obtained expression, and the new T network, while you are introducing the M, the T network has been modified like this. The M into Z1 by 2, M into Z1 by 2, then Z2 by M, then Z1 into 1 minus M square by 4M. The same techniques is applied in the phi network. If sun terms is reduced by the factor 1 by M, then to make Z0 phi, both the networks are equal. In series arm also modified like this. See here, the 2Z2 and 2Z2 has been modified like this, 2Z2 by M, Z2 by M. Then Z1 is modified like this, Z1 dash. Similarly, we are obtaining the common expression Z0 pi, the square root of Z1 and Z2 divided by 1 plus Z1 by 4 Z2. That is the general expression, the ladder circuit or pi network. So from that expression we can change the value Z1 equal to Z1 dash and Z2 equal to Z2 by M. So if we are substitute like this, we can obtain this expression. Then similarly we are equalizing the expressions like this, Z1 by Z2, 1 plus Z1 by 4 Z2, it should be equal to this expression. So that by cross multiplying and simplifying we can get Z1 dash here. Z1 dash it should be equal Z1 into Z2 divided by Z2 by M plus Z1 by 4M within the bracket 1 minus M square. I guess this was the common expression. So we are taken commonly, and 1 minus the M square. While you are making the cross multiplexing and simplification, you will get the expression like this. So multiplying the denominator and numerator by 4M square by 1 minus M square, the both numerator and denominator will get like this. The Z1 it should be Z1 dash it should be equal M into Z1 4M square by 1 minus M square into Z2, then 4M square by 1 minus M square into Z2 plus Z1 into M. This represents a parallel combination of M into Z1 and 4M square by 1 minus M square into Z2 is shown in figure like this. See here in the previous case, while we are substituting the new term, that's the M term, that pi network has been modified like this, 2 into Z2 by M, then M into Z1 as well as Z2 into 4M by 1 minus M square. So based on the relationship which we have discussed now, we are going to derive the low pass filter for the T and pi model, and high pass filter and band pass filter and band elimination filter. These 4 filters we are going to obtain the new expressions based on the M constant. As we discussed earlier, the M into L by 2 as well as M into the L by 2, 1 minus M square by 4M into L, then M into C, this expression we discussed in the T network. Similarly the pi network also we discussed. So we can consider the sun term M derived T filters to have impedance when omega in omega square infinite, it should be equal to 1 divided by 1 minus m square by 4m L into mc. So similarly here, can both the m it may getting cancelled, and the third numerator it will come, the first numerator. Then the expression is simplified like this: 4 divided by 1 minus m square into LC. Also the frequency is infinite attenuation. We can consider the f infinite is given by, if the omega is infinite, the f also the infinite. So the 1 divided by 5 square root of LC into square root of 1 minus m square. The cutoff frequency fc, it should be suffix. The cutoff frequency fc for the constant k prototype we obtained like this: fc it should be equal to 1 divided by pi into square root of LC. If it is the infinite, means the fc divided by 1 minus square root of 1 minus m square. So we can obtain from the expression, we can obtain easily the m value. The 1 minus m square, it should be equal to fc by f infinite whole square. Similarly, we can obtain from the expression, we can obtain from the m. So here the m it should be equal to the square root of 1 minus fc by f infinite whole square. So similarly, the high pass filter in the T sessions. So here also we consider for the frequencies, that is the omega square infinite, it should be equal to 1 divided by, here it is actually the L by m into 4m divided by 1 minus m square into c. So while you are simplifying this, 1 minus m square divided by 4LC will come. Similarly, the infinite frequency, the f infinite, it should be equal to the square root of 1 minus m square divided by 4 square root of L and C. The cutoff frequency of the high pass filters, we know that is the fc, it should be equal to 1 divided by 4 pi the square root of LC. Therefore the infinite frequency, that is the f infinite, it becomes like this, because here the value we can modify it, the square root of 1 minus m square into the fc. So that the m it should be equal to the square root of 1 minus f infinite by fc whole square. So for this case, the f value we are obtained, m value we are obtained in the high pass filter. Similarly, the band pass filter, here also you consider the T section, but normally the band pass filter means here we are adding the two impedance in the each side, we are adding some two components like this, the inductance and capacitance, as well as inductance capacitance. Due to the m, some value getting changed, so that the T section we have shunt impedance, let's say Z1 by m plus 1 minus m square by 4m into Z1, that is the shunt impedance, where the Z1 and Z2 are the values of constant K section. The infinite attenuation will occur when the shunt impedance like this. So Z2 by m plus 1 minus m square by 4m into Z1 equal to 0. The substitute the values of Z1 and Z2 we have. So the Z1 we know that, then Z2 value we know that. So the Z1 and Z2 value we are going to substitute in the expression. So 1 by m, here the 1 by m j omega infinite into L2 1 minus omega into L2 C2 plus 1 minus m square by 4m j omega is infinite square L1 C1 minus 1 divided by omega infinite C1. This expression we are obtained from the constant K filter. So in that case, the Z1 and Z2 value we are directly substituted in the case of m. So from these expressions we are simplifying that, and we are making the cross multiplication and eliminating some constants. Then finally we obtain like this, that is the omega square infinite L2 C1 omega square infinite L2 C2 minus 1, it should be equal to 1 minus m square by 4 in the bracket omega square infinite L1 C1 minus 1. So while you are making the simplifications, the omega square infinite, it may getting cancelled. Then L1 and L1 C1 will come, it should be equal to L2 C2, it should be equal to 1 divided by omega naught square. So from these above equations we can obtain 1 minus m square by 4 into f square by f naught square minus 1, it should be equal to 4 pi square f infinite square L2 C1. This is also we obtained in the constant K filter. This common expression we obtained the constant K filter, it is also same thing like this. So from the final expression 1 minus m square by 4 into f infinite square, then f naught square minus f infinite square by f naught square minus 1 whole square, it should be equal to 4 pi square f infinite square, then rk, then f2 minus f1, then f2 minus f1 divided by 4 pi f1 f2 4 pi square rk f1 and f2. See, this is the we are obtained from the constant K filter. This is we are obtained from the introducing the notation m. So we are equalizing the both expression, we can get it the m value. That is our ultimate requirement. That is why we are substituting the values. We are equaling both the values with the constant K as well as m. So here the m 1 minus m square by 4 into f infinite square minus f naught square divided by f naught square. It means here we are making the cross multiplications, then this expression is like this, and here this 4 pi square and this 4 pi square getting eliminated. Then here the rk, similarly here also the rk. So it may getting cancelled. So here if you are multiplying this expression, you will get the f1 and f2, then f1 and f2, that so here also the f1 and f2 it may getting cancelled. So the f2 minus f1 the whole square we finally obtain. Actually here the f2 minus f1 into f2 plus f1, that is a minus b whole square. Okay, anyhow here we are simplified and finally obtained f square infinite divided by 4 f naught square, then f2 minus f1 the whole square. From this expression you can find it out the value of m, that is our requirement. So f1 into f2, that is the f naught square. So the f1 into f2, here that f1 and f2 we are substituting the f naught square. So 1 minus m square into f infinite square minus f1 into f2, that is the f naught here substituted here. Then f infinite square divided by here, that is the f naught square. So that is the 4 f naught square. Then here also the 4 f naught square in the denominator. So both the side it is there the 4 into f naught square. So both the side it may getting cancelled. So the remaining term the f infinite square into f2 minus f1 the whole square, it is same. Then the square root of, yes, here f infinite square is there. So that square root of 1 minus m square into f infinite square minus f1 into f2, it should be equal like this. So 1 minus m square it should be equal to x. Then this expression is modified like this. Then this is like the polynomial expression, that is the f infinite square, f infinite, then the constant. So from that is the x square plus x plus constant, that like this you can consider this expression. You can obtain the f infinite value, that is the f infinite, it should be equal to plus or minus, that is the b plus or minus the square root of b plus 4ac, the 4ac divided by 2a. So we know that the formula. So based on that we have obtained the expression and find the f infinite value. So the f infinite value become like this while we are making the simplification. It's big, and we are again interchanging the value. The x into x, it should be equal to the square root of 1 minus m square. So we are substituted, and the final expression is like that. If plus means that is the f infinite 1, and the minus means the f infinite 1, and plus means the f infinite 2. So from this expression, the f infinite 2 minus f infinite 1, it should be equal to f2 minus f1 divided by the square root of 1 minus m square, because the second term, that's f infinite minus f infinite 1, this term it may getting cancelled. The remaining term is only this, so that is the f2 minus f1 divided by square root of 1 minus m square. From that we can find it out the m value, that is the need for the band pass filter. So here the m, it should be equal to the square root of 1 minus f2 minus f1 divided by f infinite 2 minus f infinite 1. This is the value of m for the band pass filter. Similarly, the band stop filter, it is the just opposite of the band pass filter. So you know that final expression of the band pass filter, that is this, the f infinite 2 minus f infinite 1, it should be equal to f2 minus f1 divided by the square root of 1 minus m square. But the same way we can derive the expression like this band pass filter. So we can discuss the directly for the final expression. So that is the condition here also the same, but here the f infinite 2 minus f infinite 1, it should be equal to f2 minus f1 into the square root of 1 minus m square. That is the actual case in the bandstop filter, but 1 minus m square, it should be equal to like this. Here actually 2 minus f2 minus f1, it will come suffix. Then final expression and final m is, it should be equal to the square root of 1 minus f infinite 2 minus f infinite 1 divided by f2 minus f1 the whole square. This is the m value for the band elimination or band stop filter. So up to this, our filter section is over. So let us summarize all the points in the fourth unit. So for the normally the filter may classified the 4 categories, that is the low pass, high pass, band pass, and band elimination or band stop filter. So in the 4 different type filters, definitions we are discussed. I hope you are understand. Then from each filter we are find out the constant K filter for all cases. This is the constant K filter for the low pass filter. It is the attenuation constant and phase shift constant expression then the inductor values and capacitor values, then cutoff frequency, then the characteristics impedance of the T network. So this is for the low pass filter. Similarly, the high pass filter also we derived all the expressions, that is the Z0 T and cutoff frequency, then inductor values, capacitor value, then phase shift constant and attenuation constants. So this all we discussed for the high pass filter. Similarly, the band pass filter also, that's Z1 and Z2, and finally we obtained the cutoff frequencies or output frequency, and L1, L2, C1, C2. Then the band stop filter also we obtained all the values, that is the L1, C1, L2, C2, and the cutoff frequencies. But here the band pass and band stop filters, there will be the filter operating between two frequency region, that is the F2, F1. That is why the notation is coming like this, F1 and F2. So the M derived filter we are obtained that common expression for the M, it should be equal to the square root of 1 by MC by n, FC by f infinite whole square. That is for the case of low pass filter. Then this is for the high pass filter. Then this is for the band pass filter. Then the last case, that is the final expression for the band stop filters. So up to this we discussed the fourth unit. If you have any doubt, please feel to ask me the comment. Thank you for watching.